Hello and welcome back. Okay, I am quite excited about today. We're going to be looking into flow control, and to do that we need to connect the results from the ALU back into the pipeline. So we have a total of 5 flags here. It's the logical carry, arithmetic carry, zero, sign and overflow. And we've got a number of spare control lines into the pipeline. So we've got 7 spare lines, 5 flags, and this video is going to be entirely about what we can achieve when we connect those to here. At the moment, this resistor array is pulling them all down. Now the top 2 we're not using again yet. I would be interested to know if anyone's got credible guesses as to what my plans are for these 2. Right, so that's the top 2 bits pulled low, and I have made up this dupont cable. Now it's done, they're connected. Okay, so inevitably we're going to spend quite a lot of time in the software side of things. Each of the pipeline stages can now examine the value of the flags. We're going to have to update the code that generates the control ROMs in order to make use of the flags, and we're going to need to add some instructions. But let's just remind ourselves of a couple of things. Now, an ALU instruction is issued in the first stage and it completes in the second. So most of these flags won't update until a cycle after we issue the instruction, and then the output flags come down to here, and they're not immediately usable by the pipeline because whilst they're used in that cycle to look up the value in the ROM, the outputs from the control ROMs are latched for the next clock cycle. So if we issue an instruction and then try and read the result of the flag immediately, that's not going to work. We have to wait a little, so we'll be talking about the implications of that. But let's have a look at the software side of things now. I did do a web search and I found this web page. It was I think the top Google search result, which is a list of the conditional jump instructions in x86. Now, x86 has 5 flags, has a carry flag, same as us. Although we've got 2 carry flags. We've got the arithmetic and the logical carry. And most of the terminology here for carry flag would apply to the arithmetic carry. Parity flag, we don't have one of those. We do have a zero flag, a sign flag, and an overflow flag. So x86 has a series of conditional jumps, and many of these are going to be applicable to us. So I'm going to use the same terminology. Now I've just got the one flow control instruction at the moment, which we haven't even tested. I'm going to move it to another location so we've got a bit of space. Okay, so there's jump on overflow, jump on not overflow, jump on sign. Now we've got these jump 0 and jump if not 0 instructions, but in x86 there is also jump if equal and jump if not equal. But these are actually exactly the same instruction as jump if 0 and jump if not 0. Now, if you think about this, the compare operation is effectively a subtract, and we're testing the flags on the result. So if I subtract A from B, and those 2 values are equal, the result would be 0. But sometimes when you're writing code, you're kind of in the headspace where you're thinking, I've compared these values and I want to know if they're equal. And then you use the JE or JNE instruction. But if you're, say, decrementing a number and you want to check if it hit 0 or not, then use the JZ or JNZ varieties. It just kind of helps the programmers write code that makes sense. But it does mean that we end up with more instructions in here than we're actually having to implement. Okay, here I'm just implementing the opcodes for all of the relevant x86 conditional jump instructions. You don't need to listen to me enumerating out the specifics of each of them. I'll provide a link to that web page I showed earlier in the description. Okay, actually I did say I would explain this a little bit more. So this file I'm editing here is the architecture definition file. Now, I have gone over this briefly before, but this is a data file that drives my assembler. So rather than try and write a dedicated assembler for this processor architecture, what I did is I wrote a customizable assembler which uses the architecture file. So when it sees a line of assembler, it comes in to here and it pattern matches against these options. So you declare your registers at the top and a few other basic things. And so if it comes across the instruction mov ra, tx, it will come down here, and then the material after the colon is what it's going to admit into the instruction stream. Now I'm gradually evolving this assembler, but it's still quite early days yet. But for simple processor architectures like this, it does allow you to add instructions to the assembler very, very easily. Now all of my jump instructions, the static jump and all these conditionals, are all going to use tx as a parameter. There's nothing to stop me adding additional variations that use different registers, but I'm not going to be building the hardware necessary to use an immediate constant. This is mostly about keeping the pipeline simple in order to demonstrate what I want without making the job too complex. I may add some additional registers to some of these. Obviously replicating all of these would use a lot of instruction space, adding a few more jumps and some of the more common ones, jump if equal, jump if not equal, those kind of ones that you use an awful lot for additional registers might make some operations simpler. Okay, now I've updated my definition file. I'm just going to run my assembler once, and what that does is it updates this file called pipeline.h, and this is a file that's used in my control ROM building code, and for each opcode I add into there, it adds an entry into this enum, and so that just is a nice shortcut for me to make a reference to the opcodes. So here is all of our new jump instructions. So now we need to go to the control ROM and work out how we're going to do these, because we've not done anything with flags before. Okay, I've just noticed this one is wrong. It's out of sequence with the others. Okay, so let's look at how I generate the ROMs from here. Now what I do is I've got this loop which iterates over every address in the ROM, calls this function called instruction after decoding the section which is the opcode and the section which is the flags, passes that into the function which returns a bit mask of all the control lines. So in here I've got a large switch statement, so I can do a case and then the name of an instruction taken from that previous header file, and then I can basically return a value which is setting whichever control lines I want at whatever pipeline stage I want. And then the wrapping code will iterate over that through all the possible permutations, save it out as 4 different files for the 4 control ROMs, and this gives me a really quite neat way of going through and generating those ROMs. Keep the comments up to date. Okay, I did already have an implementation for jump, even though I never tested it. Okay, so in this case, jump is asserting on the transfer bus TX and loading it into the program counter. Now, we do get a unsigned int for the flags passed in, but we don't have anything that defines what they are. Yep, so we've got room for 2 flags after that. These are 32 kilobyte ROMs, so there's 15 bits of address. The bottom 8 bits is the instruction opcode, and then the top 7 bits is flags. Right, now all of the previous instructions we've done have simply been returning a combination of control lines. We just OR together the bit flags from the various enums and that's resolved. But for these conditional jumps, we need to work a bit differently. So this first one is jump on overflow. This function is going to be called for every possible permutation of flags. So what we can do is actually write C++ code equivalent to what we want to happen. So if the flag's value contains the overflow flag, then we return that. Else, we want to do nothing. So we'll return that, which is effectively what our NOP was. Okay, I think we can shorten this a little bit by using some code simplification. This bit is basically going to be in common for all of them, and then this section inside the brackets is our condition. Okay, I'm going to fast forward this bit. I very much doubt anyone wants to watch me work through all the various flag permutations to implement the different conditional jump operations. It's pretty easy to work out if you go and look at the web page I've linked in the description. Well, hopefully that's going to be okay. Let's think about some code to test it. Now, one change I did make is I updated my code to support labels that point forwards in the file, so this code is equivalent to the last bit of test code I was running, but instead of hardwiring the address in there, I can use a label, so that's helpful. What we've got here is I clear all the registers, stick the address of jump 1 into TX, and then we're going to jump here. And what I want to do is stick some increments in, because I want to demonstrate something. Stick 4 of each in. Don't need to do that. So let's decrement B. I want to do jump if not 0 to loop 1. And then I'm going to do 4 increments of C after that. Right, now I've got 4 ROMs to update and the program code. Right, let's have a look at this. Now, we haven't been padding this code with NOPs like I normally do, so we're going to be seeing a lot of places with more than one instruction in flight at a time, so it's going to be difficult to follow. But I'm predominantly showing this to actually show some issues with the code, or at least issues I'm expecting. Okay, so there is our load TL, the address of jump 1. There we go. So this will be the first of the 4 XORs that's going to set these 4 registers to 0. And then that is a jump to TX. So we should be jumping to this address. And here is where we see the first interesting piece of behavior. Now, immediately after jump 1, the next instruction is inc B, but that's not what we've got down here in the fetch unit. This is an inc A, and that is the next instruction following the jump. But here is the inc B, and there are a sequence of 4 of these and then 4 of these. So we're getting a single inc A and then all the inc Bs. And the reason for this is very simple. In the pipeline execution, the fetch unit has pulled in the next instruction in the stream before the jump can operate. So that's all 4 of the inc Bs. And then the next instruction here is a move TL come with the address of loop 1. And we've got a decrement B. Jump if not 0 back to the address of the decrement B. But that's not what we've got here. We expected the jump to happen, but this is the increment C that's after that JNZ. We clock it again and we're back to the decrement B. So once again, when we've done a jump or a conditional jump, the fetch unit has pulled in the instruction following that and executes it, but then the jump happens. And that gives us an interesting anomaly here. Because we're going to cycle around between the decrement Bs and the increment Cs, when B hits 0, by the time it completes, we're already executing the JNZ. So this isn't actually going to see that 0 flag. That's seeing the 0 flag which wasn't set from the increment C that was executed an instruction before. So we keep on incrementing C and decrementing B. So our code is broken. So let's go back and see what we can do to fix it. Right. So when we do that jump to TX, we're going to add a NOP behind the jump. And down here, when we do the jump if not 0, we're going to add a NOP behind the jump. But then we're also going to add a NOP between the decrement and the JNZ. Now in all 3 places where we've added a NOP, we could add whatever instruction we want. And this is potentially a benefit for us. But if you wrote in say x86 assembler, there wouldn't be a reason not to do this. So we can do a decrement and then a jump if not 0 immediately behind it. Whereas on this pipeline processor I'm building, we need the NOP in between because we need that decrement to complete before we can do the operation that's dependent on that result. And this possibly seems very weird to you. But, and here's the big surprise, this kind of stuff is happening inside your processor on the computer you're watching this on all the time. Now, in a modern processor, what you have is hardware in the fetch unit, which is spotting the dependencies between instructions and doing one of 2 things. It's either delaying the execution of the dependent instruction, or in a higher end processor like a modern x86 processor, it's looking for alternate instructions that it can insert into that gap. So this is where you get things like out of order execution. If you've heard the term hyperthreading, what that is doing is it kind of looks like you've got more than one processor by taking all these gaps that it has to insert that we're doing manually as NOPs and stuffing instructions from another point of execution in. But that's completely out of scope for trying to implement functionality like that. So we're just going to stick the extra instructions in ourselves. Now, obviously, if I was trying to make particularly high performance code, I would, instead of putting a NOP in, I'd try and find a productive instruction to put in that place, because executing a NOP doesn't gain us anything. But what you'll find is I'll write code initially sticking the NOPs in, and then I'll go back over it and say, well, is there anything useful I can do here? In this particular case, for example, you could do something very clever, and you could put the decrement B after the JNZ, but you can only do that if you're aware of what the 0 flag is before that start point, and of course if you're happy for that loop to always happen at least once. Okay, so let's save out this fixed version of the code. Okay, so loading TL. Now that's come in 1 higher than before because we've gained a NOP. So now we're going to reset those 4. And then we've got our jump TX. But then we've got that NOP we fetched in. Might be an idea actually to create two versions of the NOP so we can distinguish between ones we've stuck in the code and ones that have been generated in the fetch unit. But then the next instruction we'd like to see is the inc B. There it is. So we've got 4 of these in a row. And then we've got the move TL, the address of loop 1. So that's going to be 2 higher than it was last time. There we go. So then we've got the dec B. Then there's our programmed NOP. And our jump if not 0 to back to loop 1. That's not what I expected. Right, so that's the jump if not 0. There's a NOP behind it. That's 5. That's move TL. So where's the decrement B? What on earth is that? There's the jump if not 0 in the fetch unit. There's our NOP. And there's this weirdo 5. Program counter's already showing the result from the jump, so it's hex address 11. That's the address of the move TL. How is that getting in there? Okay, now this is odd, and I suspect this is something that we just have to live with and work out how to deal with. So let's clock that all the way through till we get the jump again. Right, so when I clock again, I'm getting that jump if not 0. So we've loaded the value of TL into the program counter. But we've got an increment here. When I release it, it drops by 2 instead of incrementing by 1. So here's the jump TX forward. And there the increment didn't happen at all. So it looks like these counters don't like a load and an increment at the same time. I'm going to need to think my way around this. Okay, so I've had a time to think about it. Let's take a look at this problem again. Okay, so this next instruction is a jump to the address of TX. So this is going to get chucked into the program counter. And there's our problem. We've got the increment happening and the increment doesn't behave properly while the load is in progress. Now those lines aren't happening at the same time, but it does switch from the load directly to the increment with no space in between. So in hindsight, I probably should have predicted that I'd have an issue with that. Let's think about what we can do about it. The jump instructions are being processed here in pipeline stage 1, and the fetch here is what's causing us the problem. We're trying to read an instruction in, and then this little setup here is causing the program counter to get incremented. Now we do have this line here. The bus request line is a way of suppressing the fetch and increment. And it's just the increment we would like to suppress. But this line goes to both. So one way we could solve this problem is we could have an extra control line coming out of pipeline stage 1, which we then OR into that increment control. Unfortunately, we've got no control lines spare in pipeline stage 1. Now, obviously we could expand it, stick an extra ROM in there, but I'd really like to avoid doing that for a single control line. We could also kind of generate that control line because we know the address of the program counter, so we could build a little logic circuit on these 4 lines here, which are the load address on the transfer bus, and say if that's 1, which is the address of the program counter, then we don't want to increment the program counter here. So that could work as well. But if you remember, we did have an issue with this, which I still want to spend some time diagnosing, when the bus request line was going through this OR gate. Whatever we're doing there, it needs to be pretty quick, and we probably need to address the timing overlap there before we do anything else. So let's think about other ways of doing it. So we've got an instruction here doing a load, and without adding a bunch of extra circuitry, there's nothing we can do here in pipeline stage 1, but pipeline stage 2 has a control line that does exactly that. So let's be clever and think about what we can do to get that line set. Right, so I'm going to come down here and I'm going to create a new opcode, and I'm going to call it pre-branch. So what this instruction is a kind of a temporary instruction I'm going to stick in, and I'm going to put it in front of the jumps. So we actually, in the conditional jumps, we fill in that NOP that we might otherwise need under the circumstances where we're explicitly updating the flags for the conditional branch immediately before the conditional. And let's think about what that instruction is going to do. So here's the new pre-branch instruction. And what I just want to do is just singly output the bus request line. So this instruction is going to do nothing apart from raise the bus request line, which is normally what we'd do when we were performing a memory operation. So we're not actually going to read anything in from memory, but it's going to look like a memory read to as far as the fetch unit is concerned. And so that line will go high, the fetch unit won't fetch, it will output a NOP into the instruction stream. And so, looking back at our assembler files, we can remove these NOPs down here. Now putting these pre-branch instructions in is going to be a little bit tedious, so let's not do it. Let's go back to the architecture file. And even though we've added this as an opcode, what we can do instead is just output that byte for every branch instruction. So we can see there that that initial jump has the 5F in front of it, and so does this one. There you go. So this is outputting our opcodes of our program, but it's giving the bytes in both hex and binary and the address that are writing into the ROM. So jump TX is coming out as 5F60. So that's the actual jump there, and that's our pre-branch instruction. So we're kind of faking an extra layer of functionality. It does mean that our branch instructions have now become 3 cycles instead of 1. But we don't have to add those NOPs around them either. So our peak performance is lower. Now I will come back to this and give it a bit of thought, but I'm hoping this will work, and this will get us working today, and that will give me some chance to sit back and think of a better long-term solution. It's not the end of the world if we end up sticking with this though. Having a branch instruction take longer than other instructions is not uncommon in processors. Okay, so I need to update some ROMs. Let's give that a go. So this is our pre-branch instruction, and this is our jump. So now the increment line isn't high, so we haven't fetched anything. and that's at increment B. So we've got a nice clean jump there. 4 of those. So move TL, loop 1. And this should be our decrement B. And there's our pre-jump again. There's the jump. And there's decrement B again. So that's exactly what we wanted. So that's just going to loop around. So our pre-jump, here's our jump, and the 0 flag is set. Okay, I think that jumped. Did update that ROM, didn't I? So it's got the load and assert. Sanity check on this ROM. Okay, so that has behaved exactly right. I must have forgotten to update this ROM. So there's our 4 ink Cs. Now I'm off into a sea of NOPs. Okay, so it looks like that's all working. Let's see if we can write some more interesting code. Okay, let's have a think about what we can do. So, in the ALU demo, I showed doing the Fibonacci sequence in 16 bits, and it was a bit of a hack because what I did there was I wrote the piece of code that would do an iteration of the loop, and then I just replicated that lots of times because we didn't have flow control instructions. So let's write it properly. So our first value, 16-bit value, is going to be held in A and B. So we'll do the same as before. We'll initialize that to 0. As our second value will be held in C and D, and we want to make that equal to 1. So similar bit to before, we'll load the address of loop 1 in, and now what is it we do? So we want to add C to A, and add with carry D to B. So that gets us the next number in the sequence. And then we kind of flip it back on ourselves for the next value. So we're going to add A to C and then B to D. Instead of replicating the code out, we can do that. And we don't have to put the extra check in here because I know that the final iteration that overflows 16 bits will happen here. So then what do we do? Stick a couple of NOPs in, load the address of the start, and then jump to it. So we will stop once we get to the end of what we can fit in 16 bits, go back to the start, and begin again. Okay, let's get that on the run. Right, moment of truth. 0, 1. Okay, so now we're going to enter the loop. So we've got a second 1, and then we've got the 2. A conditional jump and loop back. So we've got the 3, the 5, and we know the drill here. Okay, so carries worked. It's good. So that's 6,765. $10,946. Loop background. 17,711. Yes, I admit I'm reading this off the screen because I've got a little binary to decimal guide. So then that is 28,657. So looping background. 46,368. This is the largest Fibonacci number we can fit into a 16-bit variable. So now we're going to add that to 28,657. And the carry flag is set because the result didn't fit. And the jump didn't happen. We're going to load the address of start. Jump back. And we start again. There you go, 16-bit Fibonacci sequence with proper conditional jumps and loops. Outstanding. I'm really happy with that. A couple of bumps in the road, but got it working. And that does feel quite a bit more satisfying than the Fibonacci sequence I did with just kind of extending things out by repeating the looped code. I will say this, you have to sit there with a calculator or my crib sheet to confirm these numbers are right. And what I would really quite like to see is the numbers appearing somewhere in a human readable form. And that is on my list of jobs. Now I've got long-term plans for an interesting display, but I think it would be a good idea to integrate something in temporarily that we can get some quicker output. I don't know when the PCB for the transfer register is going to arrive, so the next video will be either soldering that up or starting to work on a temporary display. But this is awesome. I'm well chuffed. Okay, hope you found it interesting. Thanks for watching. Goodbye.